we've already talked about the life cycle of stars, roughly the same mass as our sun, give or take a little bit. What I want to do in this video is talk about more massive stars. Massive stars. And when I'm talking about massive stars, I'm talking about stars that have masses greater than 9 times the sun. So the general idea is exactly the same. You're going to start off with this huge cloud of mainly hydrogen, and now this cloud is going to have to be bigger than the clouds that condensed to form stars like our sun. But you're going to start with that, and eventually gravity is going to pull it together. And the core of it is going to get hot and dense enough for hydrogen to ignite, for hydrogen to start fusing. So this is hydrogen, and it is now fusing. Let me write it. It is now fusing. Hydrogen fusion. Let me write it like this. You now have hydrogen fusion in the middle. So it's ignited, and around it you have just the other material of the cloud, so the rest of the hydrogen. And now since it's so heated, it's really a plasma. It's really kind of a soup of electrons and nucleuses as opposed to well-formed atoms, especially close to the core. So now you have hydrogen fusion. We saw this happens at around 10 million Kelvin. And I want to make it very clear, since we're talking about more massive stars, even at this stage, there's going to be more gravitational pressure at this stage during the main sequence of this star, because it is more massive. And so this is going to burn faster and hotter. So this is going to be faster and hotter than something the mass of our sun. Faster and hotter. And so even this stage is going to happen over a much shorter period of time than for a star the mass of our sun. Our sun's life is going to be 10 or 11 billion total years. Here we're going to be talking about things in maybe the tens of millions of years, so a factor of 1,000 shorter lifespan. But anyway, let's think about what happens. And so far, just the pattern of what happens, it's going to happen faster because we have more pressure, more gravity, more temperature. But it's going to happen in pretty much the same way as what we saw in with a star the mass of the sun. Eventually, that hydrogen is going to fuse into a helium core that's going to have a hydrogen shell around it. It's going to have a hydrogen shell around it, hydrogen fusion shell around it, and then you have the rest of the star around that. So let me label it. This right here is our helium core. And more helium is going to be built up as this hydrogen and this shell fuses. And this is in a star the size of our sun, or the mass of our sun. This is when it starts to become a red giant, because this core is getting denser and denser and denser as more and more helium is produced. And as it gets denser and denser and denser, there's more and more gravitational pressure being put on this hydrogen shell out here, where we have fusion still happening. And so that's going to release more outward energy to push out the radius of the actual star. But then when you fast forward there, so the general process, and we're going to see this as the star gets more and more massive, is we're going to have heavier and heavier elements forming in the core. Those heavier and heavier elements, as the star gets denser and denser, will eventually ignite, kind of supporting the core. But because the core itself is getting denser and denser and denser, material is getting pushed further and further out, or with more and more energy. Although if the star is massive enough, it's not going to be able to be pushed out as far as you will have in a kind of a red giant with kind of a sun-like star. But let's just think about how this pattern is going to continue. So eventually, that helium is going to, once it gets dense enough, it's going to ignite, and it's going to fuse into carbon. And you're going to have a carbon core forming. So that is carbon core. That's a carbon core. Around that, you have a helium core. You have a helium core. And near the center of the helium core, you have a shell of helium fusion. That's helium, not hydrogen, turning into carbon, making that carbon core denser and hotter. And then around that, you have you have hydrogen fusion. Have to be very careful. You have hydrogen fusion, and then around that, you have the rest of the star. You have the rest of the star. And so this process is going to keep continuing. Eventually, that carbon is going to start fusing, and you're going to have heavier and heavier elements form the core. And so this is a depiction off of Wikipedia of a fairly mature, massive star. And you keep forming these shells of heavier and heavier elements and cores of heavier and heavier elements until eventually you get to iron. And in particular, we're talking about We're talking about iron 56, iron with an atomic mass of 56. Here on this periodic table, that 26 is its atomic number. It's how many protons it has. 56 is, you kind of view it as a count of the protons and neutrons, although it's not exact. But at this point, the reason why you stop here is that you cannot get energy by fusing iron. Fusing iron into heavier elements beyond iron actually requires energy. So it would actually be an endothermic process. So to fuse iron actually won't help support the core. So what I want to do in this, well, and so just to be very clear, this is how the heavy elements actually formed. We started with hydrogen. Hydrogen fusing into helium, helium fusing into carbon. And then all of these things in various combinations, and I won't go into all of the details, are fusing heavier and heavier elements. Neon, oxygen, and you see it right over here, silicon. And these aren't the only elements they're forming, but these are kind of the main core elements they're forming. But along the way, you have all this other stuff, lithium, beryllium, boron, all of this other stuff is also forming. So this is how you form elements up to iron 56. And also, actually, this is actually how you can form up to nickel 56, just to be exact. There will also be some nickel 56, which has the same mass as iron 56, just has 2 fewer neutrons and 2 more protons. So it's nickel 56 will also form, can also kind of be, it'll be like a nickel iron core. But that's about how far a star can get, regardless of how massive it is, at least by going through traditional fusion, through the traditional ignition mechanism. What I want to do is leave you there and think about, just so you can think about what might happen next now that we can't fuse this star anymore. And what we're actually going to see is that it will supernova.